Bismillahirrahmanirrahim. Assalamu alaikum students. So today we are going to start with a figure, and this is a figure of an aerofoil. And you know that aerofoil is a cross section of an aircraft's wing, and this aerofoil is used to generate the lift that is required for an aircraft. So what's happening here is what we are going to see is the when the flows past this aerofoils, it tends to separate from this aerofoil and creates a boundary layer. So what is a boundary layer? If we want to see what is a boundary layer is the profile of velocity. It is the velocity profile when an object moves away from the surface of the object. So when a fluid element moves away from the surface of the object, so here we have a fluid particle, it is on the surface of the object, but as it moves away from the surface of the object, it creates a certain type of velocity profile. And when this particle of fluid attains the velocity of the free stream, like here, as it moved away from the surface of this object, it attained the velocity of the free stream. So this region here is called the boundary layer. When the fluid particles separates from the surface of the objects and attain the velocity of the free stream. So in that case, that velocity profile here is called the boundary layer. So this boundary layer separation is very important when we study aerofoils or bluff bodies, so that we can see that where the drag forces will occur and how we can reduce the drag force. So in case of aerofoil, we want this boundary layer separation to occur further down the tail of this aerofoil. We want to occur it somewhere here, because what will happen if the boundary layer separates here, it will result in an increased lift. So the lift coefficient will be higher in this case. What's happening here is the boundary layer is separating further up this aerofoil here. So this is very unwanted situation, and what it will result in will a decrease in the drag coefficient of this aerofoil, and we will have a reduced lift. So that is very unwanted situation, and we want to reduce this situation. So what happens is that we need to see that where the boundary layer starts separating for different flow conditions. That can be the velocity of the flow, that can be the density of the air and temperature, etc. But we need to do in a little bit detailed manner. We need to see that where different type of boundary layer profiles on this surface is formed. Like here you can see it is a laminar type of boundary layer formation. Like you can see here, this is the laminar type boundary layer formation. This is the permanent type boundary layer formation, because when the fluid particles that is separating here from the surface of the object attains the velocity of the free stream, it is happening in an unsteady manner. So here the flow separation is occurring in an unsteady manner, and you can see here that as the flow separates, it creates a certain amount of rotation of the fluid flow. It forms this type of rotation. It can also be seen here. It forms rotation. So when this flow separates from this surface of the solid object, it rotates, and these rotations, these small rotations, are called vortices. And what these vortices do, these vortices have their own vibration. They have their own vibration, means they have certain amount of energy, and that vibration have a certain amount of frequency. So in case of aerofoil, they result in an increased drag force, an increased drag coefficient. And in case of other objects, let's see if we have a building. If we have a small slender building and we have a flow here that flow past this building, and as this flow in the wake of the building, it causes rotation. This flow rotates. So this is the wake region, and in these wake regions, the flow rotates and causes these vortices. So in that case, in case of a building, what will happen is these vortices will apply a certain amount of force due to these vibration. And if frequency of these vibration becomes equal to the natural frequency of the building, so in that case will occur resonance will occur, and in that case this building can collapse. And in history, such type of failures had occur in case of buildings, in case of bridges. So this is very important form of analysis in which we study the flow separation from a solid object to see that how these vortices are being formed and what effect will these vortices have on the object under consideration. Again, in aerofoil, they will result in an reduced lift coefficient, and increased drag coefficient. In case of a slender structure, for example, a tall building, what will happen is that these vortices will uh, apply some forces, and these forces will have some frequency. And if that frequency becomes equal to the natural frequency of the building, then it can cause resonance, and ultimately it can cause failure. So why we are discussing this is that this sort of analysis cannot be done with the help of our integral equations. For example, that in the last chapter we derived a Reynolds transport theorem, and what we did was took a finite control volume and applied our Reynolds transport theorem on that finite control volume. So in that case, we were able to find our different flow parameters. But in these cases, when we need to see a detailed flow, like here we are seeing the flow in a very detailed, like it's separating from the solid object, it's forming a certain type of velocity profile. But to see these velocity profiles and to derive mathematical relations for these type of velocity profiles, what we need to do is a differential analysis. So we will see these type of flow and derive equation for these flows with the help of our differential analysis. So now we will not have a certain amount of large control volume, but a very small volume will be under consideration, or even a single fluid particle will be under consideration, and for that purpose we will derive our various differential equations, and we will see the conservation of mass, momentum for these differential equations, that how we are going to satisfy those principles in case of our differential analysis. So now let's move on to our main topic. So this is what we are going to do in this chapter, that we are going to analyze our flow in a very detailed manner. So for that purpose, we need to revise some previous concepts that we applied in the previous chapter. In the previous chapter, what we did is we saw the gross effects of the mass flow with the help of our conservation of mass principle. We saw the gross effects of forces on an object with the help of our conservation of momentum principle, and we saw the gross change in energy with the help of our conservation of energy principles. And what we did in the previous chapter, that we took our object of interest and defined a control volume for that object, and then what we did is that we analyzed the flow that was going in that control volume and the flow that was going out of that controlled volume, and derived an equation for that was our Reynolds transport theorem. So that analysis, that Reynolds transport theorem was in integral form. So what we did was, in the previous chapter we did an integral analysis of our flow. We did an integral analysis of our flow, and what we will do now is we will now do a differential analysis of our flow. We will see point-to-point details of our flow region by taking a small region, a very small region, as compared to what we did in the previous chapter, that we took a considerable amount of large region around our concerned object. So as you can see here, we are now concerned that what happens to this flow when it moves past this object. So now you can see the difference between these two types of analysis, that now we are more concerned that what happens to this flow when it strikes this object, what happens to this separation point, where is our separation point, how will these vortices going to be generated, what will be the frequency of these vortices. So these are the answers that we are going to answer in this chapter. And now you can see the difference between these types of flow analysis, that in this flow analysis we were not concerned that what is happening to the flow when it strikes this object, but now we are more concerned about the flow that is flowing past this object. So for these types of analysis we have our differential analysis, and that's what we are going to do in this chapter by taking a small amount of region and analyzing the flow there from one point to another. So this is what we are going to do in this chapter. So let's move forward. So we are still talking about fluid kinematics, but now we are concerned about a single fluid element, and that fluid element can move, and that fluid element will also deform. So we will have to classify that what this motion will be, and what due to that motion what the deformation will be. So uh, a fluid at time t, this is the fluid at time t, and it can move and deform simultaneously at time t plus delta t. So that is a general motion. That general motion can be a translation motion, means the fluid is moving in a straight line, or due to that translation motion it is causing linear deformation, means this fluid is also deforming linearly. So that translation motion is causing linear deformation. But what happens is the fluid can also rotate, as we saw in the first slide that a certain amount of vortices were generated when the fluid boundary layer separated from its object. So that was rotation, and due to that rotation an angular deformation can also happen. So for our fluid element that is moving in a straight line, a linear deformation will occur, and for our fluid element that is rotating, an angular deformation will occur. So to read out this statement, fluid element motion consists of translation, linear deformation, and rotation and angular deformation. So this is what we are going to do first. We are going to classify this linear motion and linear deformation, write an equation for that, and then we will see the rotational motion and the angular deformation. So here we are not just concerned about the motion of the particle, but also the deformation of the particle resulting from the particular type of motion. That can be either rotation that will cause this angular deformation, and translation will cause linear deformation. So this is what we are going to do in this chapter. So now let's revisit some of our concepts that we learned in the previous chapter, that was velocity field and acceleration field. So why do we need velocity field and acceleration field here? Because we are talking about the motion and deformation of a single fluid particle. So for that purpose what we need is the velocity, and to get the relationship between the motion and the forces, for that purpose we will need an acceleration field. So this is what we are going to do. We are going to revisit some of our velocity field and acceleration field concepts, because to get the relationship between the motion and deformation of a fluid particle, that depends on the velocity field, as you can see, because if we are talking about the velocity of a single fluid element, it means it's moving, but we are not only concerned about its motion, we are also concerned about its deformation. So for that purpose we are going to utilize our velocity field concept. So and the other one is the relationship between the motion and forces causing the motion, that is dependent upon the acceleration field, and for that we also derive the material derivative to see the change of a particular fluid particle with respect to time and its position. So for that purpose we are going to see that this is what we defined as our velocity field, that here we are representing velocity both as a function of its position, x, y, z axis, this is the position, and time. So this is the velocity field. Velocity field means that the velocity of a fluid particle depends on where it is located, and within the flow field, and when it occupies a particular point as determined by time, that at which time interval it is occupying this particular position, and this is a particular time interval. And this was our Eulerian method of flow description, as you remember. By deriving this, by taking a derivative of this velocity field, we can also find our acceleration field, and that's what we wrote. That is that our acceleration field is equal to the change in velocity, partial change in velocity with respect to partial change in time. And here is our convective change, that is the change in the position of the fluid. So this was the change with respect to time, and this was the change with respect to position. So that gave us the total change, and it also gave us the concept of material derivative, that defining a general form of equation, we can take the change, we can see the change in with respect to time, or the change with respect to position of any fluid property, and for that purpose we derived a material derivative. So the acceleration of a fluid particle is described using the concept of material derivative. And not just an acceleration, in the previous chapters we also saw the change in temperature of a fluid flow with respect to time and position. And to go through that material derivative equation, this is what was for acceleration field, but this was our generalized material derivative equation, in which we saw the total change with respect to time, and we equated that change to partial change with respect to time, and then the partial change with respect to position of that particle. And for that partial change with respect to position of that particle, we also needed the components of our velocity. So that is why we also said that velocity field is important, because to see any fluid property we need to have the velocity field to study that property. So if you are studying the temperature here, you need to have the velocity field, the XYZ components of your velocity, to see that change with respect to position and with respect to time. This was the more generalized form of our material derivative equation. This is again the partial term, and this is the velocity vector, the u, v, u, w components of the velocity, and this is the del operator that contains all these partial terms. So we are going to use these operators and these concepts in our coming slides, so that's why we needed to revise some of this. So now moving forward. So now let's discuss linear motion and deformation. In this case, our particle will move in a straight line, and along that motion it will also deform in the direction of that motion. So how will that happen? Let's look at this figure. So here we have a cube, and that cube is represented as a two-dimensional square now. So you can see the sides of this cube is O, B and A, C. So what will happen now? We are talking about motion. So this particle will move along a certain axis. So if this is the u velocity vector of this side OB, this is the u velocity vector. And if this side OB moves from this point, let's say this point 1 to this point AC, a change in velocity will occur along the change in a certain axis, and that change in a certain axis will be along a certain length. So this is the velocity gradient. Velocity gradient is the change in velocity due to change in distance. So this velocity, u velocity vector, as you know that u velocity vector is the x component of a velocity. So this x component of velocity is changing along the x component of this particular cube. If it has a certain reference point that in this case will be assumed to be a three-dimensional Cartesian coordinate system, or in this case a two-dimensional Cartesian coordinate system. This is the x and this is the y. So this velocity changes along the x-axis, and to represent this total change, it will be the sum of the previous velocity that this side OB had before translating to this point AC, plus the change in velocity, the velocity gradient along a particular axis, and the direction it covered when it moved from point OB to point AC. So this is the total change in velocity now. And from that total change, we can also see our change in volume that is going to occur, because as you remember, we are talking about motion and deformation. So this term here, this u plus partial u or partial x delta x, represents motion and deformation. So this is the motion, just to be clear, and this is the deformation. So to just get the deformation, we will do a simple math, and that is to subtract the initial velocity from this term, and what we will get is just the deformation. So this is just the deformation, and that deformation can be seen here. This is just the deformation, and to see that deformation, or to represent this deformation as a function of time, what we will do, we will write it like this. We will also take the time term, that is the change in deformation at a certain instant of time. So here we are also representing the change in volume as a function of position. This will be a certain position and time. So just to be clear, that's why we mentioned that the velocity field is very important to signify other terms. So this is the same concept that we have been talking about in the previous chapter in the start of this lecture, that we are going to represent our change in volume also as a function of our position and our time. So now we understand what these terms are and what they mean. What they are representing is what is mentioned in the topic, that is the linear motion and the deformation of this single fluid particle when we view it as a two-dimensional square. So what happens when we want to see this in a 3 dimensions? So let's add a third dimension to this cube. So this is our 3-dimensional cube, and this cube translates along a certain axis. Of course, this will be along the x-axis. This translation is along the x-axis. So if this is our points, let's specify some points. This is our point O, this is our point B, this is our point A, and this is our point C. These points are corresponding to this figure. So what is happening is the same phenomena that we already discussed. Now this face, this back face, has translated along a certain length delta x, and here at OC AC, now you can see its changed position due to change in velocity and along a certain axis, as we already represented. So this at this edge, now this edge that we talked about, this edge now has a velocity of u plus partial u partial x and dx. So just to represent the deformation, let's add another small chunk, and this is what our deformation will be. So this total now here is representing this velocity and the deformation, this whole. So this was what it will look like in a 3-dimensional view, that actually we are talking about a change in the velocity of a face of a cube, not an edge, if we represent it as a 3-dimensional figure. So this is what's happening here. So now let's write some terms, some equations for this to get in equations for this linear motion and deformation. So the change in volume occur. This is the volume. This will be the volume of our cube if these are the sides delta x, delta y, and delta z. If this is the volume of the cube, so this change in the volume will be equal to this term. So now let's look at this term. You are already familiar with this term. This is the change. This is due to this term, the whole volume is changing. The whole volume is changing. So due to this term, the whole volume is changing. So with delta x, we will write partial u over partial x. So what does this term mean? That the change in this length, that this length is caused, or this length is, or the change in this length is due to the change in the velocity of this fluid, and that velocity is the x component of the velocity. So change in the x component of velocity of this fluid particle. So if there is an x component of velocity of this fluid particle and it changes along an x-axis, so due to this change in velocity along an x-axis, this is the velocity gradient. Due to this velocity gradient, we will get a change in this length, delta x. So due to this change in velocity along a certain axis, that is the x-axis, we will get a change in this length, and due to change in one edge of the cube, due to the change in the length of the one edge of the cube, the whole volume of the cube is going to change. So this overall changes. This term here is responsible for the change in volume of this cube. Obviously these cubes will have other sides, that is delta y, delta z, but the particle is not assumed to be moving along these axes. So the change in volume is occurring due to the motion along the x-axis only, and due to the corresponding change in that edge, that is the edge along the x-axis, and as a function of time, that this change is also occurring at a specific time. So this is what we did. We also represented the change in volume as a function of its position and as a function of its time. So now let's see the rate of change, that if you want to see the rate of change, that how will with the passage of time, how will this volume change. So let's write an equation for that. So we will derive the rate of change equation in volume from this equation. So what we will do is we will combine these terms. These terms are equal to delta v, we already know, and we will take this to the left hand side of this equation. So if we take it to the left hand side, so what we will get is the 1 over delta v. If we take this term to the left hand side, so we will get this term, we will be left with partial u over partial x delta t on the right hand side. So what we will do, we will divide this term by delta t and divide this whole term by delta t. So this is what we got. This is how this equation got here. So this is the change in volume with respect to time, and this is the again the change, the component that is causing the change, its change in length or change in velocity in a specific axis with as a function of time with a change in time. So this is now the term for change in volume and if we want to specify this term in a form of a sentence, so this will be the right sentence, that the rate at which the volume delta v is changing per unit volume due to gradient partial u or partial x. So the rate, this is the rate at which the volume is changing per unit volume due to the gradient partial u or partial x. So this is what it comes out to be, that is equal to this term partial u over partial x. So this is our rate of change of volume per unit volume. So if we want to see what will happen when this particle's y component of velocity changes along a y axis, if this particle z component of velocity changes along a z axis, So then what will happen to the volume, and how will we write an equation for that? So as we know that due to the change in volume along a single edge, along a single axis, was equal to this, that is the change in velocity, that is the particular component of velocity, the x component of velocity along a particular axis. So for the whole change, for the change along the y and z axis, this will also be equal to these two terms. These two terms will represent the change in volume in the x direction and the in the y direction and in the z direction, and this term, as we discussed already derived, is the change in volume in the x axis. So this is the rate of change of volume per unit volume of the whole fluid particle will be equal to this term, and we can also shorthand it and write it like this. This is the del operator. This del operator contains all the partial terms, partial over partial x plus partial over partial y plus partial over partial z. This is what this del operator contains, and this v velocity vector represents all the components of the velocity, that is uv and w. So we can separate these two and write it in a more generalized form. So now let's move further and discuss this final equation that we derived a little bit more. So this is what we derived in the previous slide, and this is the rate of change of volume per unit volume, and this is also called volumetric dilation rate. Actually, this is what the change in volume is, and the rate of change of volume, as we would like to call it in simple terms. So how will this volume not change? Will be for incompressible fluids, because we know that in incompressible fluids the density is not changing, the density will remain constant. So what is density there? That is the mass per unit volume. So if mass per unit volume is not changing, so the volumetric dilation rate will be 0, because the element volume cannot change without a change in density. This is a very important point, you have to keep that in mind. And let's see what linear deformation is and how we defined it. So linear deformation was equal to these terms, as we saw that was linear deformation is equal to the change in velocity along its particular axis. So that is the change in the x component of velocity along the x axis, the change in the y component of velocity along the y axis along the and the change in z component of velocity along the z axis. So if the velocity changes along its corresponding axis, so that will be linear deformation. But what if the velocity changes other than the axis that its component is in? So what will happen? So in this case, the u velocity vector, that is the x component of velocity, is changing along the y axis, and here the y axis of velocity, that is the v unit vector, is changing along the x axis. So this is called cross differential. This is called cross differentials. So this cross differentials will cause angular deformation. So this is what our next topic is, angular deformation. We have derived a term for linear deformation, and now we will see how will we define angular deformation. So this is our angular motion and deformation. What we have here is the same fluid element, and now what is happening to this fluid element is these two sides, that is OA and OB, is going to rotate. So this is the u velocity vector of this fluid element, this is the v velocity vector of this fluid element. So this OA rotates to a new length, that is OA dash. So it makes an angle of delta alpha with this x-axis, this edge, as you can say, that delta x. So now the velocity gradient is partial u over partial x, that is the partial change in velocity with respect to the x-axis along the edge length, that is delta x. with respect to time delta t. So what's happening here is that is the u velocity vector, and that is the v velocity vector. Means this is the y component of velocity, this is the x component of velocity, and this OA edge is attaining a new position OA dash by moving in this direction. Means this velocity increasing along this edge like this. So in the x component of this velocity is forming a gradient along this edge. So this is what this equations represents. This term represents, that is the partial change in velocity. That is the partial change in velocity. As you see this gradient, this is the partial change in velocity along the x-axis. This is the x-axis. So that this edge OA can rotate to this new point OA dash. I've also put this picture of boundary layer. As you remember, in our first slide we discussed boundary layer, that from this point where the particle is at rest, it attains the velocity of a flow stream. So up until the attainment of this velocity, it forms a certain profile, and this profile is called the boundary layer. So as you can see, this velocity direction is along the x component of the velocity. This velocity is in the x component as it is denoted by u, but this gradient is with respect to this y-axis. So this is also what is happening here. This velocity is forming a profile with this x-axis. So this is what this gradient will represent. This is our velocity gradient now, and this velocity gradient will cause deformation in this edge, that is delta x, with respect to time delta t. Similarly for edge OB, this will be our velocity gradient. So in this case, our edge OB moves to a new point OB dash, and the velocity gradient for this edge is partial u, that it moved in the that the velocity vector for this is the u component of velocity, that is the x component of velocity, and this x component of velocity forms a gradient with this y-axis, of this fluid element, and causes a change in the delta y edge of this fluid element with respect to delta t. So this is our fluid motion, that is our angular motion and deformation simultaneously. This is our deformation now, and this is our motion and deformation combined. So now let's write some terms, and before that let's look at the 3D representation of this motion. So this is the original fluid element, and as it rotates to this new position, as you see in these dashed red lines. So this is our O, A dash, and this is our O, B, and B dash. This is our u velocity vector, this is our v velocity vector, and this element, this edge OA that has a length of delta x, it attains a new position OA dash because of this velocity vector v, as it forms a gradient with this edge delta x. So this velocity will have a gradient of partial u of partial x, sorry, partial v or partial x, because this is the v velocity vector, and for the edge delta x with respect to delta t time. So this is again our position and time. So similarly for this length OB, it moves to OB dash, and correspondingly it forms a velocity profile in this direction of the u component of our velocity vector, and this profile is made with the length that is along the y-axis. So this gradient is partial u over partial y for the edge delta y with respect to time delta t. So this is what our angular motion and deformation will look like in 3 dimensions. So now let's look at some equations. This is the rotation for edge OA, and this rotation is represented as delta alpha over delta t, that is our change in angle, that is the angle that edge OA dash makes with the edge OA, that is this angle divided by delta t. So this is the rotation for OA. This angle can also be, we can also find a term for this angle delta A by taking a tangent of this small triangle here. If we take a tangent of this delta alpha of this small triangle, that is this small triangle, so we will have this term, that is the tangent of this angle will give us perpendicular divided by base. So this is our perpendicular term and this is our base term. So this will come out to be partial v or partial x delta t. So now we can write our rotation for edge OA in these terms, in the terms of our velocity gradient and time, and these terms will cancel out and this will come out to be a velocity gradient cross differential, because as we mentioned that this change in velocity is not along its axis but along the axis that is making a 90-degree to this velocity vector, that is the x-axis. So the y component of velocity is changing along the x-axis as we mentioned right here and here by taking these gradients and representing it in terms of velocity and its change along a corresponding axis and with respect to time. So now let's see the rotation for edge OB. So as you can see, this will be the change in this angle, that is our angle delta B, this angle with respect to time, and we will find this angle with our tangent theta by taking this triangle, that is this triangle, and it will come out to be partial u over partial y and delta t. So putting the delta beta in this term, so what we will have is, that is partial u over partial y and delta t over delta t. So these two delta t will cancel out and we will have partial u over partial y for our rotation of the edge OB, that is again our partial change in velocity vector u, that is the x component of velocity, and this partial change occurs along the y axis as we mentioned here, that this gradient is created along the y axis of this element. So if we would like to write a combined term for OA and OB, we can do that, and this will represent the rotation of these two edges along a certain axis. So this will be the z axis, and if we take the average of these two velocities and add them, that is the rotational motion, angular motion of edge OA, and that is the rotation motion of edge OB, and by adding them and taking their average, what we will get is the rotation along the z axis. As you can see here that these two edges will rotate, that will have an axis perpendicular to these two edges, and that axis will be the z axis for this edge OA and OB. If we can draw a z axis to these two, so this will be the z axis along which this OA and OB is rotating. So we can combine these two and write them in terms of omega z. So this is the rotation along the z axis. Similarly, we can write equations for the rotation along the x axis and y axis. Let's have a look at them. So here we have our rotation along the z axis, that is equal to these velocity gradient and this, and our rotation along the x axis, in this term we will have our velocity gradient, that is the change in the z component of the velocity with respect to the y-axis minus the change in the y component of the velocity along the z-axis. So again, if we take our rotation along the y-axis, so that will be the partial change in velocity, that is the u vector x-axis of the velocity, and along the z-axis, and this is the z component of the velocity change in the x-axis. So these terms omega z, omega x, omega y represent the rotation along the x, y and z components. So these three components can be combined and written in this form, in the ijk form. So we can do that, and we can also write it in a more generalized way by taking the 1 over 2 term out and writing it in terms of this, that is omega is equal to curl, that is the curl is for the del operator here, because this curl will represent the cross differential, that we have all these differential terms. This is what it will represent, and these are cross differentials, and when we take its cross product with the v velocity vector, that is the, in this case that will be u v w, but they will be this will be a cross product, not a dot product. So the result of only those components that will make a 90-degree with each other will come out to be positive, that will be 1, and those components that are parallel with each other, they will come out to be 0. We can also write this in the matrices form to get a better idea of this. So here, if we take the cross product, what we will get is this term, these terms. So you can see right here that these are the terms that we wrote here. So this is the omega x, this is omega y, and this is omega z. So writing this in a more generalized way, we can represent this with the vorticity, as we mentioned in the first slide, that we can also write this, that is omega, but if we write this in terms of 2 omega, this 2 will cancel out and will come out to be here, and this 2 omega is called our vorticity, and this is the symbol for vorticity. And vorticity is defined as a vector that is twice the rotation vector, that is the rotation vector that we use throughout this derivation, and this rotation vector is equal to this, as we know. So why are we multiplying by 2? Just to make it a little bit neat. There is no significant reason behind this, but the scientists that like to use this vorticity equation will like to have it this way. So since the factor of 1 by 2 is annoying for them, many workers prefer to use a vector twice as large called vorticity. So vorticity is twice the rotation vector. So this is our definition for vorticity. This is what represents the angular motion and deformation. So this is what it represents. So hopefully this was clear.